Okay, hi. So we were talking about the failures of the hydro turbine systems. So in the previous part of this lecture, we talked about the failures or the damage to the surface that is caused by the cavitation process, and now we are going to talk about the erosion process. So as we discussed before, there are four categories of the damage or the failure of the hydro turbine systems: cavitation, erosion, material defects, and fatigue. So now we talk about the second one, that is erosion. Now cavitation also ultimately leads to material removal. So you can also say that is a type of erosion. But what we commonly use the term erosion for is when the particle that is hitting your surface, they are solid particles. In the case of cavitation, you have gas bubbles or vapor bubbles, and that is why we do not call it erosion. However, by definition, the erosion itself is the damage to the material or the material removal caused by the collision of the solid particles or any foreign objects. Okay, so this can cause a damage to the hydro turbine systems. However, we have talked about erosion also in the context of wind turbines. We have also talked about of erosion in the context of gas turbines, where you have unburnt carbon particles that will hit onto the blades, and they'll also cause erosion. So erosion, not just for the turbine systems but also for a lot of other machinery, erosion is one big problem, and we all understand it. It is something very obvious to us. It is something that we kind of always expect. However, the mechanism of erosion is much more interesting than you think, because often it happens that we do not really think about the mechanism of this process. Think about it this way. Let's take an example. Okay, let's forget about the sand particle or small particles. Let's take an example of a bigger particle. Let's say a bullet. A bullet is being shot at a human being. Not the best example, but a bullet is shot at a human being. It will pass through the human being. I'm thinking of human being as just a material. Now, if you hit the bullet onto a very thick Pelton wheel, which is made of a metal, what will happen in that case? The bullet will not pass through the wheel. It will probably create a dent or a pit and then bounce back. Now, if the bullet is being hit not from the 90-degree angle but from another angle, let's say 30 or 20 or 10 degree, what happens then? The bullet might just touch the surface and leave. The bullet in that case will spend some time, fractions of second, but will spend some time on the material, maybe create a scratch or a dent and then leave the material. Now, if you hit a brittle material with the bullet, let's say you take a clay pot and hit that with a bullet, what happens then? The pot will completely shatter. So now there are so many things that are influencing the damage to the material caused by a particle. A, the velocity of the particle. B, the angle at which the particle hits the material. And C, the material itself. The material itself, if it is brittle or ductile, it will have different, it will experience different type of damage when it's hit by a particle. So it's the same thing can be, the same concept can be transferred to the erosion that is happening in the case of turbine blades or any other machinery for that matter. Now, coming back to the turbine blade, coming back to the hydro turbine blade, what happens? Why does erosion create? Why are we, is it just the surface damage, or can it really lead to the overall breakdown of your turbine system? So what does erosion do? It removes some material. In the case of hydro turbine, you sometimes will see the damaged blades for which the huge part of the blade came off as a result of erosion. So basically it is material removal or chipping which can then change the flow pattern of the water. And when the flow pattern is changed, then you will have the overall loss of efficiency. You can also have vibrations. oscillations of the entire system, and that might lead to the final breakdown. That might create some additional damages to the system. So ultimately, the corrosion can lead to the final breakdown of the turbine system. So we take an example of the Francis turbine. What happens in the case of Francis turbine? You may also have the clearance gap increased between, for example, the guide vanes and the plates. And when the gap is increased, that also changes the flow pattern. You may have cross flow, for example. You may also have the changed overall velocity profile, and that is how it can lead to the final breakdown. Now, as I mentioned before, ductile and brittle materials behave differently when it comes to erosion. So in the case of ductile materials, the mechanism of material removal is plastic deformation. The material undergoes plastic deformation. Now, in the case of brittle materials, that is not the case. What happens in the brittle materials, that when your particle hits the brittle material, cracks are formed and the material experiences damage because of the intersection of these cracks. Now, depending upon how strong are these cracks, how large are these cracks, and what is the intersection pattern of these cracks, you may have complete damage to the material. It may completely shatter at once, or very small parts of the material will be removed, and over a long time, then you will call it an erosion. In the case of ductile materials, however, what you have is material removal by the cutting action of the particle that is hitting. Now, also we talked about the angle at which the particles hit. So it has been studied that in the case of ductile materials, the angle of where the maximum erosion takes place is about 30 degrees. However, that is the angle in the case of brittle material is 90. So if you plot it, it will look something like this. So angle of attack is plotted on the x-axis, and you can see the erosion rate for ductile material or ductile type of erosion or brittle type of erosion. So you can see that the peak for ductile erosion is around 30 degrees and the peak for brittle erosion is around 90 degrees. What is also very interesting is that for all ductile material, the mechanism of erosion is very similar. It doesn't matter what is the thermal conductivity of your material, for example. It doesn't matter what is the electrical conductivity. So it doesn't matter on other properties of the material. As long as it is ductile, for most of the ductile materials, you will have pretty similar mechanism of erosion. Same thing also for the brittle materials. You will have a range of brittle materials will deform by the same erosion mechanism. So what are the influencing factors? We already talked about some of them. So let us summarize. Number 1, particle velocity. Number 2, the angle at which the particle hits the surface of the turbine blade. Size of the particle. This is something we haven't discussed yet. And the distance traveled by the particle on the surface. So this fourth, the last one, distance traveled is related to the angle of impingement as well as the velocity. Angle of impingement, because when particle hits from a side, it will probably stay a little bit. For a while it will stay onto the surface and then leave the material. So now let us talk about the particle size. If you think about it, it's very trivial that if you hit something with a smaller particle or a bigger particle, the effect is going to be different. But let's talk about sand particles, particularly in the context of hydroturbines. Let's say there are sediments that are mixed into the water and they are hitting your turbine blade. It turns out that the optimum size for maximum erosion is between 130 to 200 micrometer. When the particles are much smaller, let's say 1 micrometer, then they are practically harmless to the turbine blade surface. At the same time, if you have really millimeter scale particles, so you have stones, they are also relatively harmless to your turbine blade. But when you have this 100 to 200 micrometer particles, then you will your blade will experience maximum erosion. So now when we know all of these things, let us think about how can we prevent our material surface from getting damaged. So what happens, or what is usually done, is after the manufacturing of the blade, you will do some erosion testing. There are equipment available known as erosion test rig. So what you can do is you can change the velocity of the particles, you can change the angle of the particles, and you can find out what is it that is causing the maximum damage to your material surface. You can factor in these things into your design, and you can also, if possible, change the jet angle accordingly, because the waters of different places are different. The composition of sand in these waters are different. So accordingly, also the particle size, maybe some water has all particles, or say 70% of the particles of the sand that are within the 100 to 200 micrometer range. Maybe some waters have only very small sand particles. So accordingly, you can perform these tests and change the design. You can also use anti-erosion coatings. This we also discussed previously. And of course, you have to do design optimization, factoring in all of these aspects. You can also use low sediment water. In fact, it is preferred that you use low sediment water, but this may not always be in your hands, because as an engineer, you may be given the job to design the turbine for a certain location, and you do not have the control. However, one more thing that you can do is you can try to attach a filter where at least the larger particles are removed, and also, if possible, if it is suitable to the flow of water, then you can also try to remove the particles that are in the size range that is most damaging to your turbine blade surface. Okay.